I'm glad to stand here and to be able to address some things to you. I would like to bring you to my world. That's an engineering world. It's a world of application. And I warn you, it's the first time I stand here because the last year we met with Andy and Peter in the evening, and we were wondering what we are going to do next year. And then I spoke of Bionics, and I did not realize that I was the one standing here, one of them. So be careful what you say to others. The subject is how and what creation teaches us to solve mechanical problems. I took a citation from Max Planck, and I will address it to you without comment. It is the constantly ongoing, never-ending fight against the skepticism and dogmatism, against unbelief and superstition that religion and science wages together. And the trend-setting watchword in this fight has always been and will always be towards God. That encouraged me for this talk, and this is a very prominent man, and you can think of it your own. I have 4 points. An introduction to bionics and structural mechanics. I would like to compare it and to bring you in my world. Then I go on and show you what are my personal contacts and experience with bionics and what I'm working right now with bionics. You will not think that it's bionics, but I will explain to you. And then how we, and I put it in brackets, can learn. I will show you the way the engineer has a systematic approach to learn from creation, or my colleagues would say from nature. They will never use the word creation, they will say nature. Then I will bring some examples. So, bio-inspired areas in civil engineering. The first 3 I will address to you. That's structural design, especially the main subject in this talk is structural design, material design, these 2, and monitoring. Then energetic design, for example, maybe termites. We learned a lot of termites for air conditioning and energetic design of buildings. And if I have time, I tell you, I met a guy on a conference and what I experienced with him in this field. He was not a believer. Then acoustic design. I always complain our teaching rooms, because we have to speak so loud that the pupils may hear you. The acoustic design is not very good in our university. Sustainability, a very interesting subject, but it's too much to show here. And preservation design. So, first of all, what is bionics? Actually, we in Germany, we use bionics, and the term is claimed to come from Germany, but it's not true. The first man who took this word in a presentation in 1901, and the next one in 1960, but even they are not the fathers of bionics. In Germany, and this is the rule in Germany, it's the combination of biology and technology, and we shorten it in bionics, but you cannot figure out who was the first one who uses it in this way. But interestingly, bionics has a different meaning in the English-speaking zone. In America, for example, some people sitting here come from America. They knew the series, The Bionic Woman. It was sent in the TV in 1970, and in this, it's artificial body parts, and in our days, it's artificial organs. This is not meant by me if I speak about bionics. And the Cambridge Dictionary from 2011, the science of creating artificial systems or devices that can work as parts of living organisms. The definition I use is equivalent to the English one, biomimetics. And you find the word mimesis, that's a Greek word, to imitate. You imitate, and that's equivalent here. I use it, bionics and biomimetics is for me as the same word. And here you find the definition in our codes, VDE, that's the Association of German Engineers. They have or DIN ISO, and the official definition is that Bionics technical discipline that seeks to replicate, increase, or replace biological functions by the electronic and or mechanical equivalent. And when Peter introduced the subject, he took a word that no bionics people would like to use, that we copy. We do not copy. That's not the goal. We imitate, or we try to abstract it and use some principles. And I will show to you some very basic principles that everyone of you in school must know of. There's another word you get confused in the world of bio. It's everything is bio. And one word you come up with, biomimicry, I cannot spell it the right way, maybe you can tell me. Mimicry, it's a philosophy in that interdisciplinary design approaches taking nature as a model to meet the challenges of sustainable development, social, environmental, and economics. So I will start to bring you to my subject with a tree. What a tree has to challenge, what are the challenges for trees? There's, in the first place, the so-called dead loads, self-weight. If you take me as a tree, I have two arms, and I look like a tree. I have to bear my dead load, and that's permanent. Then life load, if I take this cup, you see a life load. This cup is a life load. It adds something to the dead load, and I have to keep it in balance. And I'll speak about this a bit more. Then wind loads, not permanent. Sometimes you have, sometimes you have not. Come to Magdeburg. I invite you to visit us, and you will experience a lot of wind. A lot of wind. Snow and ice, not permanent, but a heavy load. Thermal loads, winter, summer, and dynamic loads. I'm especially interested in earthquake engineering. I'm teaching earthquake engineering, and that's dynamic loads. Well, some basics from mechanics. Gravity. All the time we struggle with gravity. If I train this arm to get more strength, gravity is the one that is the challenge. It's working all the time. You cannot switch it off. It's all the time there, gravity. And what we try to do is bring it to an equilibrium, that we can endure it, that we can bear it, that we can take it. And yeah. Connected to this is force and deformation. For example, these are some utilities I can show you. This is, I apply a force, and the cause is deflection. The force is here, or I show it to you. This is the dead load, and it bends already under a dead load. And if I put at the end, let's say rubber, it will bend more. This is a life load. And a structural engineer always has to struggle with forces and deformations, but forces are the integral of stresses. No structure, no person has forces in themselves or experience forces, but it's always a stress, it's a distribution of forces. And I show you here as an example, the dead load of a tree. You see a tree without leaves. Then I would like you to focus here. If I cut it in this height and all the upper part is summed up as a weight, I can put here on the stem, and this is the dead load of the total tree. And the equivalent of the force is the stress inside the tree. And this is the equivalent to this force is a strain. And the simple formula is you divide the cross-section, the total weight by cross-section, you get the stress. So, and the equilibrium is the ground has to equilibrate these forces. And if you have no ground, and that's already a spiritual application, you need a ground. And for us, you need Jesus. You need the ground standing on. And everything, and this is one message I try to transport to my students. You need a ground. And I ask them, what ground do you have? What ground are you standing on? So that's a bit more complicated, but I already explained it to you. A tree has live loads, and now you see the leaves and, for example, an apple. And the same picture, I cut off the rest of the tree in this part here. I cut it off here. And the total weight of the tree is here. And it produces a commonly distributed, evenly distributed stress. But now, I'll come back to this here, this cantilever. It's called a cantilever. And let's say I'm the tree, and I have a trunk here, and you put the load on it. Then you experience something that's called bending. And bending, it's nothing other than stress distribution changes. You have, if I bend it here, everyone knows, or my students, I will show you an experiment, and I ask them to put their finger where they expect tension and where they expect compression. And I'll come back to this. So there's bending that causes a not evenly constant distribution, but as shown here, a distribution changing from the positive to the negative one. So, and we have to bring this also into equilibrium. So it's not just the force that's straight on to the ground, but you have bending. You have to ensure that this tree will bear bending. So he has roots. Another example for you, you must be rooted in Jesus. You are founded on him, but you have to have roots. That's essential for everyone to have roots. So next thing, there's wind. That's an interesting load because it's sometimes there, sometimes not. The pictures are my own design. And what I would like to show you here is I call it the intelligence of a tree. Because it grows, and after some time it figures out where the wind comes mostly from. And it's developing its skin according to the loads. And you get closer rings the more often the wind comes from a certain direction. And you can see it in the shape of a tree. If it's always in the wind direction, it's bending down. At the sea, you can see it. And if you cut it, you see the rings, the tree rings are designed to be there where the maximum stresses are. I always asked my engineers, how do the tree know? In a sense, what's the nervous system of a tree, at least? How can you figure out that this is the case? And that's very, very interesting. So, and then the next step is we observed especially trees, and this is the work of a colleague of mine. He's a theoretical physicist and is an expert in tree statics. And he developed he's a fracture mechanics guy. Most of you will not know what this is, but I brought you something with me. This is my equipment for my Yes, for my lectures, I explain something, and if you try to sleep, you have no chance. So, but I take this off so to show you what I painted on here. This tree, let's say, has several branches, and they bow down, and the other side also. And you try to get them into equilibrium, and the stem has to do this. But there's a certain point, in the mathematical sense, we call it singularity. And if you have singularities, you cannot bear it. No material in this world will bear the singularity, the mathematical singularity. So another intelligence of a tree is, he figures out how to distribute the material that the singularity vanishes. It's incredible how it knows, and we learn of it. And everyone will know what will happen if I tear this apart, it will crack here. And this is principal stress, it's infinity in this, and the tree is so clever. And this guy here, Mr. Matek, he had a whole theory and called it the axiom of uniform stress. It's a further, when I finish my talk, I will come back to this, the axiom of uniform stress. It seems that nature, I call it nature for you because I could always say creation, the creator designed it, and it's so incredible that the tree knows how he should order his material and how he should grow in many aspects. So this distribution of stresses is every structure, every creature tries to get uniformly distributed stresses, not to have this singularities. So the next. This is the jump to the engineering world. So switch off everything and now explain to you how engineers deal with their real-world structures. This structure you see here is a beam. When you come in here, you are walking under such beam. You see one here, that's a huge beam. And it's the same, the mechanics will happen here. And remember the tree always. Stress, there are two kinds, tension and compression. There are maybe singularities you have to face, and I show you how this structure will bear their loads. They have the same loads. We have all the listed load for the tree are the same for civil engineering structures, completely the same. So I show you now I brought you something with me, and if someone is interested in this cookie, he has to answer one question. So that's a cookie. It's a layered one. And what do you think we'll expect if I bend it? What will we Pardon? In the middle it will what? Break. Why?
Tension is too much.
Ah, well, what do you say? Why does it break in the middle? What is the cause? Okay, you are a psychologist, I don't. Oh no, I know. I know I cannot offend her. Okay, so I asked Andy. Oh, sure, it will break in the middle. Because what does this material not have, or not have enough, the capability to take tension? I break it. And we do it all every Sunday, we break bread. This is not tension, it's not very good intention. So an engineer has to deal with this because concrete is a very, very good compression-taking material. And what an engineer has to do, he has to think about how can I do this. So everyone of you will know how it is done. Inside this, rebars in this structure. We enhance the capability of taking tension where tension is, and we place there rebars. Reinforce it. But I want to show you, if you just are concerned with the stress in the middle and you will get it to equilibrium, you put in a bar there and it will work. But that's not the whole truth, and I will show you. If I take a very heavy sack and try to put it in this, keep it here. I'm the tree, I'm equilibrium, and bring the load down. But there's a material-dependent parameter and behavior that most of the people don't like. And unfortunately, I have no burger here, because with a burger, you can very good show what's happening. If you have a burger, and it's a very good burger, you have a lot of sauces, a lot of cream and and you put it in your mouth and you buy what will happen? Well, it's going aside. And this effect, it has every material. You push it here, and perpendicular to it, it goes this way. And therefore, if you look at TV and the heavyweight people, they have a belt here. Not because they are freezing or something, because of this behavior. You push here, and perpendicular to it, you get stress, positive stress. That means tension. And concrete, no, it doesn't like tension. Why I last so long on this? Because this happens in every structure, in every animal, in every creature. It happens the same way. Simplified mechanical truss model. Engineers model behavior. And they try to reduce the load-bearing system to the essential parts. And I brought you, because this morning I took off my shirt and I realized I have this structure here. Do you realize this structure? You use it this way. You put loads on here, and where is compression and where is tension if I hold it here and you put your coat on? There are three arms, and where is tension and where is compression? Okay, you're a physicist. You made okay, the load is here, and it tends to have the pressure here. The other way around. If I take this load and put it here, then it is the same. So, and the engineers found out we have to have at least this struts and this tie, so we can bring to equilibrium. But again, the most important thing is, the founding. You need a foundation. So now I'll show you what we can do against this failure. What I can do if I am a heavyweighter, I take this belt so that I cannot break in this direction. I saw once an Olympic one, and I don't know the Eingeweide, what's the intestines. They came out because he forgot his belt. He wants to this way. So, and what kind of the engineering solution to this? They are clever enough. They build belts in this structure. Not only this load-bearing tension, but everywhere a belt. So look what happens when this is the model we developed as engineers to keep this failure from happening. There's tension bars low, and the red ones are the compression bars. And to get the load from the lower parts to the upper parts, we need this blue ones. They bring up the load that tries to break out at the upper bottom line and bring it up. And the model is called a truss model. I will show you many truss models in nature, because nature does it automatically. And it puts the material exactly there where it needs for compression and where it needs for tension. This is what you have shown, and this is the model we use to bring a simple beam to equilibrium in all periods of his load experience. So this is the so-called reinforcement. And you see the upper part, these are the bars for tension, and this perpendicular ones, this belts, they are exactly belts. They put belts around so this failure cannot happen. So the next step, these are the rudimentary structural elements we use in structural mechanics. And the beam I explained to you the truss structure. The more complicated one are walls and slabs and shells. I come to this, but I will not explain it because it's a bit more complicated. But the very foundation, stress, is in all the structures the same. I explained to you two-dimensional, or sometimes one-dimensional. If you have a strut, it's one-dimensional. So we go on, and I go through, this a bit faster, because you have the foundation now in an engineering sense to understand what's following now. There's a person I got to know during my studies, this Joseph Monnier. And if you are German, you may know Moniereisen. Ever heard this word, Moniereisen? This is to credit Mr. Monnier, Joseph Monnier. He has the patent of reinforced concrete. And the next one, I learned him personally, and I learned from him to build shells. This is Mr. Isler. I will show you. He's a well-known engineer worldwide. He constructed beautiful structures, shell structures. Then this colleague, Mr. Matek, I got to know Mr. Baumgart on a conference, and he told me about his examinations of a tiger claw and what were his outcomings. And then I will show you what I'm personally doing now. I try to give this beam, this very beam I showed you, a nervous system. Well, this is Mr. Monnier. In 1867, he had the problem, he had pots made of concrete, and if he put them down too fast, or they fall, let's say, 20 meters down, they always crashed. And he was annoyed about this. So he thought about what I can do. And he worked in a botanic garden. And this, how it's spelled, Opuntia, cactus. He realized when they get dry, they have this structure inside. And this is a network, a net. What's missing? The flesh around is not very good in tension. Pressure, quite good, but tension not so good. So, and when he looked at this here, he got this idea. Oh, I have some material that's good in compression. What helps this material to get better in tension? So he laid wires in it. And that's he invented the so-called reinforced concrete. And I work all day long with this. So that's the slide with health monitoring. And you see here not only the bars that on this and this belts, but this blue lines. And this is this, I call it the nervous system of these here. A year ago, I started a research project when I got inspired by a technique that is laser dependent, laser and fiber dependent, and I show you how it works. It's called, it's based on so-called Rayleigh scattering. You have, let's say from telecom glass fiber, you shoot in with a laser a certain light, and then this fiber has the characteristic of scattering light, and you can measure it. And the change in refraction along the fiber is a measure of the strain or of the temperature in that. And we as engineers are deeply interested to get our structures a nervous system that we know when it will fail, when it needs repairance, and therefore a nervous system. 15 years I studied systems, and I only could listen to, let's say, a 200-meter bridge at several points. And that's quite not enough. You have to listen to every single, the crack, you don't know exactly where it will come. So you have to have a nervous system. And this is combined now, I combine this with this new methods of machine learning and intelligent design to train my nerve system to figure out what's going on. And the end will be to develop new materials. And this one here is the next. We embed it right now in streets because we do not know exactly how streets fail. We know, and you experience this all the way, you have to wait so long because all the streets are damaged, and we try to figure out how it happens. And we put a nervous system in this part of the street, and you see it. That's in Magdeburg in our lab. Behind our lab, I built this in the street. So, learning from a cabbage leaf. This is one lesson I got from Mr. Isler. And he learned us the most important thing. And this lecture, this is the introductory lecture for the Bionics lecturing in my university. And what I want to get to is they took off their smartphone and don't look at the smartphone, but that they look at a cabbage leaf. I was trained this way. What shall they learn from a cabbage leaf? Well, Mr. Isler showed us what he learned from the cabbage leaf. And the construction you see here, that's a shell structure, a very thin concrete, or in this case, wood structure. And he got the idea to do this way on looking at a cabbage leaf and imitating, mimicking these bars here, these trunks, this system. And he got up with very efficient structures. The next very intelligent idea he had, he experimented with sheets and nets. And what he did is, he showed us, it was winter, and he showed us a movie he took in his garden. He hung up this sheet, then he took water and spread it over it, and it froze. And the shape remaining is what you see. Then he took it perpendicular, 180 degrees, and he had a perfect shell structure. So he learned by gravity on this sheet with frozen ice. It was a very clever idea, and he designed, and this picture here, he explained to us how he got the idea and how he realized it in this structure. And this is another example of a very well designed and very thin, it's concrete in this case. It's reinforced concrete. It's a very, very clever to do this way. So then the next is a tiger claw. And here you see something at work that's it's optimization. A very huge field in my engineering work is to find the structure with the fused material, but the maximum unload-bearing capacity. And this guy here I met on a conference, and he explained to me the so-called soft kill option. What this is not that important, but it's an optimization method. And he made his PhD in the optimal form of a crane hook. Here I overlaid it with a crane hook that we use every day. And I asked him, what's the perfect? He took 3 years PhD, and he found out, he could have more easily. He could have looked at the tiger claw because it was the exact form he got out from his mathematical investigations. It was the perfect form with the minimum material. So, and here this structures, he invented, or his professor, he invented the method called soft kill optimization. That's an iteration process. Here you see a cantilever that iterates for the load. You apply at the end the load, and the structure resulting is the minimum structure in terms of material. It's very clever, and you can see it all over in living structures. This here is, I think it's Ukraine, I think. It's Ukraine. Seeigel. Sea Ukraine.
Sea urchin.
Urchin, okay, thank you. Sea urchin. Well, I learned them next. So, and now how we can learn. There are two methods in the engineering world, systematic and engineering approaches, and I go through this very fast because I want to show you the examples. There's the so-called biology push-up or bottom-down design, and the other one is the technology pull-down design. My wife told me to tell you, if you read this slide, because she is a translator, and this is the official document from the VDI, from the Association of German Engineers, and you find so many mistakes in translation and even German words in this translation. So she asked me, raise your hand for me, and this is not my work. And yeah, you start with the biologist. He gives the analysis of the structure, and he shows you as an engineer what is this structure built of and what is his capabilities, and explains the system to you. Then the engineer is listening very, very carefully, and he hopes to grasp some ideas of it. And then they together develop methods that they can use. It's never a copy. It's always an illusion, or you get an idea. But we want to systemize it. So we set two people together, the biological approach and the engineer listening. Or the other way around, the engineer, this is the technology pull-up or bottom-up system engineering. The engineer has a problem, and he is figuring out how I can the solution. Maybe there is a solution already in biology. And he asks the biologist, and there are databases. I go through this a bit faster. You see these two approaches are actually working now. And I show you a real-world version here. This is all the structure I will show you. You all know these windmills. And they are seeking for the optimum foundation of it. And they have databases of diatoms. And if they search for a solution for their how to design it, they use databases of this diatoms. Here you see the momentary structure. This is the way they build it. And they want to optimize it to get a better solution to this. And these are the steps they are going through. They are screening databases with structures coming from, you know them from Ernst Haeckel. He published a book, Nature, and he draw very, very incredible good pictures of living creatures, and especially these diatoms. And we now use it as a source, a screening source, to get to a structure. And then we evaluate it. That's the structure assessment. This is the database. Then we evaluate some. We find out, oh, that seems the optimum in nature. Then we do the abstraction and analyze this with certain opportunities we have, so models will fit. And then we come out at least with the assembly and the optimal design for this. And then we use it to build the next optimized structure. So I'm back to the presentation now, to the examples. So examples, I think the most of you know, all know Mr. Eiffel. Maybe you and your wife visited it once. We did. And he constructed Mr. Eiffel. He's not the engineer who did the construction, but who sold it. And it was in 1987, and the centerpiece of 19 World, what's the name, Fair. And he got the engineer, Mr. Coquelin, a believer. I know some of his relatives. He invented this structure based on this. He took, everyone here in this room has at least 2 of this, I hope so. And what you find is that this is a bone. And all that I explained to you in the beginning of my talk, the stress distribution and where is the maximum compression and tension and so on, you can see it optimized in this bone. And these trape cellular things, this is a microscopic build of it. They are built of rods and plates. There are 2 elementary structural elements we build our houses with. And they are combined in an absolutely optimal way so that the minimum on material is used and the maximum on load bearing. And the bone knows, as the tree knows, where it has to concentrate the rods and plates and where it can spare them. The so-called wonder of Jena, an engineer who first mimicked the so-called, this is a Kugel, well, what's the, so this is a sphere, and it's built up of the triangular elements. And the mimic is from the left to the right. And this structure is incredibly strength, stable, very efficient in material, versatility and energy efficiency and scalability. So now I come to the Eden project. In England, I think you should know it. And there you can see sea urchins, sea urchins, I cannot remember. Sea urchins, how they are put on shore. It's very beautiful, very sophisticated boat. Up to now, we don't really understand how it works, because in this state you have it, it's dried out, and it's fragile. It's not very load-bearing, but if it's in a living structure, it's amazing what it's doing. And it's compounded in platonic forms. Here you see 5 edges, and this structure is not a copy, but it's mimicked the sea urchins. And the last one, or I have only one in addition. This is what you have, the so-called tensegrity structures. These are structures that are found in your very single cell. The analysis of the cell structure gives, many of the biologists suggest this, and the engineers agree, that there are a strut tie system. And it's very capable of, yes, you can do that, just push on it, and that you can deform it in an incredible way. And this is, our cells are built with this. And there are pressure struts and these tension bars in every cell. And the structure is called tensegrity. And here you see a bridge that is built. And this is, actually it's kind of copy. And here the marine radiolaria, that's a living being where you can see it working, how the structure is built of this tension and compression bars. It's very, very intelligent. It's a special mathematics behind it, and it's mathematically completely solved how this works. And it's incredible deformable. And the last example I will show you, when I came here before, Alexander visited us, and he asked me to, maybe there's an example that I can show where there is something already developed in technique. Can you find it in nature? Yes, you can find, but much more sophisticated. And what I can show you is excavator arm versus spider leg. The same principles are working here. It will take too long because I would give you time for discussion. The same principles, you have a hydraulic jack to move the arm in the right direction and to make it working in tension and compression. And you have to have hydraulic cylinders that can tear and pressure. And the same you have in the leg of a spider. You can, if you look at a spider and you found it dead, maybe you learn to look where are the legs when they are dead. This is, let's say, their legs, and where you will find them when they are dead. Nearby. Why? Why the hydraulic is away. I called it the blood, the liquid is away. So the liquid that makes, from the body, it gets pressure, this liquid, and you can stretch it and take the pressure off and you can move it. And if it dries out, the leg is at your. This is nearly one-to-one copy of an excavator arm. And I would like to invite you to the virtual exhibition. Everyone, you can visit it in the internet if you like. You can go through this and look at many different examples, incredible examples that I cannot show. I will end up with two spiritual applications. When I studied the first time reinforced concrete and I became a believer, I realized, and I have to do a lot as an elder in my church, to bring people to equilibrium, to reinforce them. And every one of you needs reinforcement. And if you don't know the loads that make you break, you should figure out what make you breaking. And then you should figure out how can I equip myself spiritually to get not cracked, to get not damaged. And you have this foundation in the Lord Jesus Christ. He is the foundation, and the Holy Spirit is the reinforcement in you. And you have to activate it all the time. And you have to, when I saw the first time with more intelligence, this, maybe you remember it, this beam here, and it explodes, suddenly it sprang over. This happens in many people who do not realize we call it burnout this day. We call it burnout because they do not reinforce in the right way. If you are reinforced, you can maybe resist these forces.